I think that we have one last numerical example left for the GMM. Okay, so today plan is we finish this example, and then we will go to the some notebook example. Okay. So we have two ways to do clustering. One is the centroid way, which is a k-means, and then the GMM, the mixture of Gaussian mixture model, and both the philosophy behind or under is very similar, right? We start with some random guess, and then we try to, based on that guess, we do some assignment, and then based on the new assignment, we try to update our initial guess and repeat until it converge. Okay. So any particular questions? If you have, you can. Is a good time to ask. Is any especially for the mixture Gaussian part? Are you okay with after you go back? Do you have any confusion? Any difficult part to understand? Yes, this question. Sorry. Oh. I think we will see that a few examples during when we do the Jupyter notebook, as you can see that here. For the particular model itself, are we okay? I know the k-means is pretty straightforward, but for the mixture Gaussian, are we okay with that? So please, always, if any question, please stop me. And now we just try to have a very small example. We try to say, okay, we have 5 points, and we try to find the Gaussian mixture model for this data set with k equal to 2. As I mentioned, usually the k is predefined for the algorithm itself. Of course, how to find k is another story. We will have the example to show how typically we will find k, and also during the slides we do mention there's some kind of near point. Remember, there's some points which will make the change become a little bit more slow, or then that transition point usually will indicate what is a k. But usually when you run either the k-means or run for the GMM, you need to specify what k you want. Okay, so those algorithms require k as an input. So now we start with a initialization. Okay, those initialization is just your random guess. Of course, different random guess. Maybe some will be superior than the other. So how to pick a good random guess, then this is another different story. But you do expect to give some random guess. Okay. So remember, we have for each Gaussian, for each component, you need to calculate what is a mean, what is a variance, what is a weight. Right. So basically the mu, sigma, and pi. Okay. So now at the beginning, we will assume both components are equal like. Okay, so we assign 0.5. I guess that is a very good initialization. Then you assign 1 and 1 for your standard deviation. Then this 2 value is a kind of randomly selected. Yeah. Then we suggest there's a threshold to be 1. Because remember when to stop, right? We do this EM step, right? We iterate over this E step, M step, E step, M step. When to stop? The judgment we need to make is to say, hey, when the change become really small, because at the beginning your random guess is too off. So each time you do a EM, you will expect some great change, decrease about your log likelihood. Remember, we take log pi of your likelihood. Remember that. Then also it's important to realize why we put log there, because we want to convert a product of everything into a summation of log. That, yes. Yeah. Usually yes. Usually yes, because this is a cool part about the those why we like, for example, like k-means, because as I mentioned, if you the matrix, for example, there you're using your Euclidean distance as your metric to measure the distance. Usually those methods will guarantee it will converge. Yeah. Yes. Yeah. So that means the converge. What that converge means. So a lot of algorithms they don't converge, and certain algorithms they converge. So we for those, I mean, there's people who try to analyze the convergence of those methods. For those methods, we really like, we love them, and we adopt in real world. Usually, they will converge. Yeah, but sometimes converge to a bad solution. That is possible. But for example, like k-means, if you choose bad initialization, you might converge to a bad solution, but still it will converge. Yeah. Yes. So what's the point where the model eventually converges? Converge means it's stabilized. It doesn't. It's happy with the current solution. Um, you can't bring them further down, but that doesn't mean it's a like a global good solution. Yeah. Usually, yeah, there are not many. Honestly, for this part, I never do a theoretical understanding about or analyze about the k-means based on what I'm read. Is you might have a couple of different solutions, but it's not like you start with a different initialization, you will end up with different things. It's not. Yeah, more or less they will converge to a very similar set of solution. But how many solutions there are, I need to go back to really look into what is other people's study result. But in general, don't be afraid. Those are the very stable method. You just run 5 times. I'm sure you will get probably the best solution you are looking for. Okay. And it's rare. I remember I used k-means so many times. It's rare you will really ends up with something really bad. Yeah. Unless your data is bad. Your data, we will show some examples. Certain data is by nature is not fitting to the k-means. Like in the example I was mentioning, the reason why, for example, I'm looking into, let's say, a subspace clustering. If you think there's a 2 lines, if you do k-means, of course, your upper part is one cluster, lower part is one cluster, right? It's obvious, right? If I have 2 lines, think about that. You based on the distance, of course, those points will be one cluster, those points will be one cluster. But we know there's a shape, right? There's 2 lines. Obviously, you need to put one line into one cluster, another line into another cluster, right? So then this will bring the limitation to, let's say, if you run k-means on this type of data, obviously you won't get the result you want. So which is the reason why we are bringing model. I mean, including the Gaussian mixture model, we are bringing a model. For example, now you are thinking, let's say, a strip of points, another strip of points. If you do k-means, then again, the upper part will be one cluster, lower part will be another cluster, basically. But now if you say, hey, I have a Gaussian in mind, so probably you will nicely separate them because they are a kind of two cluster of Gaussian points. Yeah. So all those is the reason why sometimes this works better, sometimes this works better. There's no general solution to say it works for every day, all the data. So this is a tricky or the fun part about data science. A lot of time you really need to look at your data and see, hey, what is it? I need to understand the data. Then you apply the best method to do. Yeah. Otherwise, we do not need to do machine learning, but just take one method and run for all. It's not that case. Yeah, but today's deep learning is a little bit that flavor. You just give me billions of data. Let's say Google, they have 10 billions of data points. Then just running through a neural network, then they get their result. Yeah. So that one looks like it's not the trends usually the machine learning people like to see. So then honestly, when the deep learning come out, we all feel a little bit worried because we will think we will probably lose a job as a researcher because you just running a neural network looks like it solve everything. But later, then we figure out it's not the case. You still need to understand the data, understand the model. And the neural network, a lot of time, neural network give you the result, which is not necessary the true solution we are looking for. So there's really no easy solution for this. Yeah. So good. We still keep our job too as a human. So what we do here is we basically try to repeat the E step and M step, these two iterations. Honestly, I would really encourage you because for these two, for this particular question, I would really encourage you go back to actually take a piece of paper and work it out. This is really a very simple example. Yeah, you just follow, just go back and apply this two calculations. The first, you try to randomly start to assign you get the mu, you get your sigma, you get your pi, right? Based on your random initialization, right? Now what you want to do is you're plugging into this formula. You try to compute how likely a data point fitting the ice component. Because now in this example, k equal to 2, so we have two components. You have component 1, component 2, basically Gaussian 1, Gaussian 2, right? So now you have 5 data points. So you need to compute for each data point, what's the likelihood that points come from a particular Gaussian component, right? So basically you need to compute gamma gamma 1, 1, gamma 2, 1. Then gamma, the I here indicates a component in here. So then you compute the gamma 1, 2, gamma 2, 2, then gamma 1, 3, gamma 2, 3, and so on. So basically you compute for each component, each point, create this likelihood. Okay, once you have all the gamma, are you following this? Right. So because for each data points is you just plug in, right? You have data points. This is a Gaussian function, right? You know mu, you know sigma, you know pi. You can definitely compute this, right? Then the denominator is basically you compute this for each of the component. Then you just add them, normalize it. Yeah, so very straightforward. So after you compute this, for this particular, you have two components. You have 5 points. You compute this basically the 10 gamma value, and then you will just go to this stage. First, try to adding all data points. Because for each data point now you associate with some of the likelihood for each component, right? You just iterate over all data points, and that's I lose. Okay, then that will indicate some kind of the total likelihood for data points belong to the i's component. Here is you have n1, n2. Okay, then you try to normalize a little bit because the n will be your total data points. You just see after you divide it, you will get, hey, actually the component 1 have this weight, component 2 have another weight. You have a pi 1, pi 2 in this case. Okay, then use that. You just try to recompute all the mu by plugging because you have everything you need. Then you recompute what is the reweighted the variance. Okay. So after you get that, you just repeat. But of course, for each time you want to compute your log likelihood. The log likelihood is what we compute like this. Sorry, you compute your log likelihood is something like this. initially this part is likely after you decide the mean and the variance, you know, and also the pi, you know what is your mixture, Gaussian mixture looks like. That is a kind of density function. Okay, so if you plug in your xj, you will know what is the likelihood, right? So you try to multiply them. So basically you will get the accumulate. But the multiplication, as I mentioned, when you multiply a lot of small numbers, you will get a super tiny one, which is a lot of them, the computer is difficult to handle. The computer is difficult to handle super large, super small. Like you have 0.10, I mean 0.000, then the computer probably will lose the precision. Yeah. So what we do is you take a log, then you convert it into a summation of log something. Then this will be your likelihood. Then you just see when the change between the iterative, between the adjacent iterations are smaller than certain tolerance. For example, 1 here, then you stop. Okay, so with this, I will encourage you just to go back to plug in the data and see, do you have any difficulty? All right. Did everybody follow this systematic way to do this EM, right? Okay. So just go back. If you have difficulty, raise that during the next class. I will try to come back to this example again. Otherwise, I will try to show you some Jupyter Notebook examples. Okay. So again, we will use sklearn to do our k-means. So basically, you import the k-means from sk.cluster. So first, we try to generate a set of data points, and then we try to plot them. The scatter is a very good function. Scatter is try to plot those data points on a 2D or 3D space. So we will see, hey, this is a data point, and how to find cluster among those data points. All right. And again, as I mentioned, you need to specify what is a cluster. Yeah. Okay, I remember we have mentioned this function, but we have a lot of more options. Let's go back to that one. Yes. Yeah. This is an actual function. It contains more parameters. Yeah. Again, for those functions, we usually during the class we will just show you some typical way to use them. In order to really see what is the option there, please do a search, do a Google search about this particular function. Usually, you find online manual, which will give you all the possible argument you can input to the k-means. For example, here you will have this is a this is an n cluster. It's like how many cluster you want to have. This is like the k, right? The k we need to specify. Then the second one is n init. If I remember correctly, this is try to specify how many times you want to run this algorithm. Yeah, just go back to double check if what I'm saying is wrong. Please correct me during the next class. But my understanding is that if you put 3, probably your algorithm will try 3 times to avoid those bad decisions. Yeah. Then the random states, this is a more try to set to some value so you can control the method will try to converge to a very similar solutions. Yeah, you can repeat your solution in some sense. Yeah. But again, I talk this out of my head. If you found what I'm saying is not correct, please correct me. Yeah, but because typically when I myself running the k-means, usually I need to set the random state to be or the random seed to be a value, because I need to be able to repeat the same solution. Really depends on your the random state of your computer. Those kind of randomized method may give you different solutions. So each time you want to reproduce certain result, you need to fix those random seed. Yeah. Then you try to call the fit, which is try to fit, basically to fit your data into a model. We have seen this a couple of times, right? Regression, we also call regression.fit. You try to do a kind of training there. So then you have labels. Labels is basically your clustering assignment to data. Okay, and also the cluster centers. Cluster center is basically those centroids you finally agree on. So let's after we remember this method, let's come back to here. So here we didn't use much of the more sophisticated arguments. We just say, hey, k equal to 2, and then we fit the data. Then we try to print what will be the class center, what will be the label. As you can see, the class center now is this 2 is our class center, because you have x, y two labels, and then we have a class label. This is like the label you are assigned to your x. So if we plot them out, as you can see now, we have this is a 2 centroid we find, and this belong to one cluster and this belong to another cluster. Looks like a pretty reasonable solution, right? And then let's try another. We change our k equal to 5, because as I mentioned, at the first place, we need to decide a k. It's our job to decide a k, right? So you can, because when you see this data, especially when you see this data, how many k there? Maybe the k2 is a good guess, but sometimes when data is complicated, we don't even know how many clusters there. So in this case, we made a bad decision. We say, hey, k equal to 5, and we try to do the k-means. We fit the data. Then you can say we get 5 clusters, and then this is our assignment. Now, as you can see, this is a result when you k equal to 5. Those cross means the centroid. So as you can see, it's not a good result when you pick not the appropriate k. Okay. But really, this is because this is simple, it's obvious. But in real world, when you see some complicated data, it's really not obvious what is the most optimal k. So sometimes it's a hard decision. Some certain and many times. Yeah. So here we try to write a little bit more code, but you can try to read a little bit. I think that there's nothing fancy there. We try to show the iterations. Okay, so this is during the first iteration, and we get something like this, and then we do iteration 2, iteration 3, iteration 4, iteration 5. Yeah, the cross sign indicates the centroid. We each time we re-evaluate. Okay. So this give you a rough feeling. It's like exactly like what we try to talk during the class, right? You start with something, and each time you assign, then recompute, then reassign. And the fancy part is that this k-means is a good algorithm. It will converge to a pretty good solution. So after you're doing this, if you recompute and reassign, more or less your solution will not change much, right? Do you agree? Because because there's no much distance you can re-optimize, right? So it's a very smart, simple and smart method. But sometimes, for example, here we have obviously we have a solution we are expecting in mind, right? When you see this, obviously there's a four cluster. So it looks like we indicate, because we have 4 colors here, we do indicate for k equal to 4, but it turns out at the end it gets something like this. So this is a bad solution I was mentioning. Yeah, it's not super likely. If you run k equal to 4, a lot of time you will get what you want, but sometimes you will get bad things here. So for example, this is a if you compare these two, as you can see here, okay, this is explains, yeah. So here is this is a k equal to 4, right? Init you say random, and the n init equal to 1. So that means we just doing initialization for once. We only running once. And as you can see here, this is a random state. This is exactly what I tried to say just now. We are set random state equal to 104. That is, we are hand picking, like we are probably, when we try to find, I did, it's not somebody else create the example. I mean, when he want to show this, probably he will try random state equal to 0, equal to 1, equal to 2, until try to 104, then he find a bad solution. So this random state disturb how do you do the random initialization, right? Because in the computer, there's some random number generated, which control a lot of random initialization. Okay, I hope you get a flavor there. Yeah, because a lot of times when you really, for example, you want to randomly pick some number, but actually that is not a true random. It really depends on some of the random seed in your computer. Right? Probably depends on your time, depends on what. So here is we can try to play with a random state. You can find a bad initialization. But if you say number initially equal to, let's say 3 or equal 4, you try it multiple times, probably you will skip. This one will looks, anyway, you will have a very large distance loss for this solution. So this will be discarded. Okay. So which is the reason you probably want to run this method multiple times. And here is so if I don't have understanding about the data, I don't know how to choose the number of the cluster. If I say k equal to 9, you will end up something like this, right? So of course, for this simple case, we can use the philosophy behind this near point to say this is not a good solution. Because for this part of data, you can say you can increase your k equal to 2, k equal to 3, and keep increasing. I'm sure when you say k equal to 9, for example, the loss or the distance does not be much lower than the right k equal to 5 case. Because as you can see, all those additional clusters, they are all subclusters. Because you have a class center here or class center here, which doesn't cause much change to those subcluster data. I hope you see that. So which is reason why you see a job then very stabilized decrease. So then that transition usually indicates what is the right K. At least for this simple case, that method works well. Yeah. All right. Any questions? Okay. So yeah, this is a one example I was had in head to say why we want a model based. Because if you have two stripe of data points, if you do k-means, obviously this is a result you are expecting, right? But this is not uh, what we are looking for. So we are looking for those is one cluster, this is another cluster. So k-means has some limitation if we are particularly have some for those data have some different structures. Okay, so for this case, the GMM, the Gaussian mixture model will be the solution. All right, so let's look at some example about the Gaussian mixture model next. So here we are using sklearn a mixture. We import Gaussian mixture, and we try to, as you can see here, this is what I try to say. Usually when we, I'll say, doing some analysis, we like to have our result to be repeatable. Because in order to be repeatable, usually you need to using the same random initialization. So to make sure your random generator probably start from the same state. Okay, so which is reason we say seed equal to 1. That will try to make your randomize, although still is kind of random, but this random is repeatable. Okay. Then we will try to generate the 3 Gaussian and we concatenate them. So now we don't really know those points are actually from a Gaussian. We just see a bunch of points. Okay, and then this is what we try to say is we have 10 components. Okay, we will try to fit model with 1 component, with 2 components, because now we pretend we don't know how many components are there. We try each of them. So we will try to generate a number from 1 to 10. So now the K array equal to probably 1 to 10. There's 10 numbers there. So each of them will be indicate one of the component. So then we will try to iterate over these 10 numbers, and we try to get a different mixture model, and with the n component equal to 1 and equal to 2 equal to 3. So basically what we did here is very simple. We just try to get 10 models. Each of them have a different k input. All right. Are you okay with following this? The last line, we are okay, right? This is a okay. This is some complicated function, but more for plotting. You can read a bit. I mean, there's nothing fancy there. Then here we just try to show for all models, because we know there's 3 components inside, right? When we generate, we are generated from 3 Gaussians. But we pretend we don't know. We want to set k equal to 1, k equal to 2, k equal to 3 to try to fit the data. Okay, so now k equal to 1, as you can see, given the data, this is what we are going to fit. Looks pretty reasonable, right? So this is but of course we see another mode here. So we are missing this tiny small cluster. So when you k equal to 2, you will get something like this. You will get this, you get this. But now when k equal to 3, hey, looks like pretty good. Because you get this one, you get another one, you get another one. So this is just give you a flavor, give you a feeling how exactly we are trying to look for we are looking for a number of components and then shifting around and then adjust their height a little bit and to see how it contribute or explain your current data. All right. So then when k equal to 4, we start to see it is not optimal, right? Because for example, in the middle you have 2, which doesn't explain your data the best, and then k equal to 5, k equal to 6, k equal to 7, k equal to 9. So of course, when you increase your component, probably the likelihood will be more or less very same, because you have more component to fit. You will expand your data anyway. But this is more like the overfitting type of things we are talking about, right? You start to using a much complicated model to fitting. Remember the curve we have when we are looking for the near point. We have a decrease, then stabilize, but probably you will still see a tiny decrease there when you increase your model complexity. Just like a k-means, if I say 100 cluster, probably that is will give you a very small error. Right? I mean, in the extreme, you say each point is a cluster center. Let's say you say if you have 100 points, I say I have 100 clusters, so each point will form a cluster. That's fine. That is perfectly minimize your distance, right? You'll get a 0. But is that a good one? Yeah. So because it's not, because you are over-explained your data. Does that make sense? Yes. Yeah, exactly. That is what I try to mention next is so usually, which is the reason why we need a ridge regression, right? Because you have regression, the first model is try to minimize your the mean square error, but the second one is try to constrain your budget about parameters. Same thing here. If you think now the k equal to 1 equal to 2, this is a budget. So now you want what you want is you want the best explain your data. You fit your data most. At the same time, you want your the k, the number of parameters, to be small, right? Is that the same philosophy behind, right? So what you want is you want to find not only fit the data most, but also you want at the same time the k need to be as small as possible. That will be a good model. Yeah. So how to do that? This is a little bit beyond the lecture we present. I think that in the lecture we didn't present this, but I think that this is good to know. There's a different criteria. The different criteria. This is those are very popular or very famous criteria like AIC or BIC. Those are the criteria. Those criteria you can find any machine learning book probably in the first one chapter, the first 1 or 2 chapter, you will find the definition of those. This essentially try to say, I not only want to minimize a loss function, but I also want to minimize a model complexity function. So you will have 2 terms there. Just like our MSE thing, your L2 norm of your weight, right? The second one, if you think about the weight regularization as a kind of model complexity, they are more or less talking about the similar things. But here you can think about the AIC or BIC, they are slightly different definition, but more or less measure very similar stuff. So now if I doing this, you can see, hey, this become clear, right? When you k equal to 3, actually you are get the best balanced in terms of this explanation or this loss function plus model complexity. So we want minimize a loss when you have a minimal model complexity. So using that AIC or BIC, is we can clearly see, hey, k equal to 3 is a very good choice. All right. So, and also this, if you're using the sklearn, this AIC, BIC a measure, a matrix building inside the package. Okay. So now, okay, so now you can try to pick the best fitting using AIC and try to say, hey, this is will be our best GMM. So this is what is the actual explanation. All right. So basically, you have a 3 model, and the 3 models through a weighted mixture, you explain the black curve. So now look at this one. If you K-means do this, if you using a Gaussian mixture to fit, you will get something like this. Yeah. So for certain data, Gaussian mixed model do have a advantage. All right. Any this is pretty cool, right? This. Any questions about the I think that we finished this clustering. So any questions about the clustering? Okay. So after this, next week we were talking about inheritance, but I want to talk first about the supervised clustering. Sorry, supervised classification. Yeah. So this is probably one of the most fancy part of machine learning is how to do supervision and then try to do classification. The classification is probably one of the most important topic, at least in my opinion. Yeah, because classification is trying to say what? It's trying to say, hey, I have give me some data. I want to assign a category, for example, and this can be extend to a very useful, many useful applications. For example, now let's say object recognition. It sounds like a very fancy, right? You see a cat picture, you say this cat, dog picture, this said dog. But what they do there is a classification, right? You are classify those images. I always say, you give me a cat. Instead of actually, I really see a cat there. I try to say, hey, this belong to the cat category. This belong to the dog category. All right. So actually, the object recognition is a classification problem. Then, for example, face recognition. So this is actually very impressive. Like now, the face recognition is one of the most impressive application in vision nowadays. Is we do really able to differentiate maybe so many large populations. You show me a face, then I say, hey, this is who. But this is, in some sense, you are also considered as a kind of classification problem. You have a lot of classes. But then you have many of those, including like you're turning left, turning right. This is a prediction, right? But you can also consider that as a classification problem. You want to, when you are your mounted camera, see the street, see the line, or see the pedestrian in front, then you want to say, I want to classify this example to the left category, to the right category. So a lot of things you can reduce to this kind of classification, which is reason make this classification a super important and super useful application. So I just give you hint you a little bit, and we were going to release a new homework, which is this is a complete new homework, probably next week, which is about the supervised classification. So because this is a new, if you guys find any errors, please report it, and please bear with us, because a lot of time we do careful proofread, but we can't catch all the errors there. Yeah, so all right, have a nice weekend.